This video is going to go through Le Chatelier's principle for AQA GCSE Combined Science and Chemistry. If you haven't already watched the video on dynamic equilibrium, make sure you've gone through that one first. You're also going to need to pause this video at different points to do some questions and make some notes, etc. from the screen, so make sure you've got a pen and your exercise book. The video is going to cover position of equilibrium and what the term means, Le Chatelier's principle, and factors that affect equilibrium. We're also going to briefly look at industrial equilibrium reactions. Position of equilibrium is a term that you'll hear a lot, particularly in mark schemes. When the forwards and backwards reaction rates of a chemical reaction become equal, the reaction is said to be equilibrium. Now, if you're unsure about what equilibrium is, you need to go back and have a look at the video on dynamic equilibrium first. So if we take the example A plus B forming C plus D in a reversible reaction, we can look at a graph. Now, at this particular point, the concentrations of all species in the reaction will remain constant, but not necessarily equal. The reaction may go nearly to completion, with barely any A and B left, or it might only progress a little, with a small amount of C and D produced. So to look at those two scenarios a little bit more closely, if we take scenario 1, producing lots of products with only little reactants remaining, we can represent it like this. I've made A and B really small to show that there's not very much of those, and C and D really big. Now here we'd refer to this as the equilibrium being to the right. Or the right hand side is favoured. So that's two ways of just describing where the position of equilibrium is sitting. If the products are being favoured, the equilibrium sits to the right hand side. In scenario 2, where the reaction hasn't progressed very much and not much product has been made, I can represent it like this, with a large A and B showing that we've got lots of that, and C and D being very small, just showing that we've not made very much. In this case, the equilibrium would be sitting to the left, or the left hand side is favoured. To take that a bit further, we're going to look at changing the conditions, and changing the conditions of a reaction can move or shift the equilibrium to favour either side. So once a reversible reaction has found equilibrium position, we can impose changes upon it. We can make changes to the reaction that causes the equilibrium to move, and to go from sitting on the left to the right, or from the right to the left. Now if we take the reaction here, if we were to increase the rate of the forwards reaction, we will move or shift the equilibrium to the right. It would cause the position of equilibrium to move more towards C and D and produce more C and D. We could also look at the reaction where we increase the rate of the backwards reaction, and that would shift the equilibrium left, because it favours the formation of the reactants. Now, Le Chatelier's principle is something that's really important, and it affects all reactions that reach equilibrium. And we can relate it to something very real life. If you get a bit too warm, you will make an action to cool yourself down. It might be to go and get a cold drink, it might be to open a window, it might be to take off a layer. If you get too cold, you do the opposite. You might turn the heating up or put a jumper on. What you're doing there is you're making a change to make yourself more comfortable, to get yourself back into an equilibrium situation, a comfortable temperature. Now obviously there is an element of thought process going on there. You have to actively go and choose to have a cold drink or to add another layer of clothing. And chemical reactions don't think. Le Chatelier's principle is something that applies to all chemical reactions automatically. It's something that just happens. And it's another definition that we have to learn. A system in equilibrium will oppose any change imposed upon it in order to regain equilibrium. We're going to look at that more closely as the video progresses. But very simply, if the concentration of a reactant or product is increased, i.e. we add a load more into the closed system, the equilibrium will shift to the opposite side, either favouring the forwards or backwards reaction to get rid of that reactant or product. If we increase the temperature of a chemical reaction, the reaction will shift its equilibrium position in order to decrease the temperature again. Now, as I said, it's not a conscious thought process that the reaction takes place, it is just something that automatically happens. If we increase the temperature, the reaction will decrease it. If we increase the concentration of a reactant, the equilibrium will shift to decrease the concentration to regain an equilibrium position. It won't be the same equilibrium position, but it will be a new equilibrium. So to look at concentration first, we're going to look at a general reaction here, A plus B forming C plus D again. If we were to add more A to this system, what will the system do in response? Well, the system will try to decrease the concentration of A. That's the first thing to think. Le Chatelier's principle tells us that if we impose a change, the reaction will oppose that change. So by us adding A, the system will try to decrease it. So how will it do that? Well, quite simply, the rate of the forwards reaction will increase. Now I've shown this with an increased size of arrow. You don't have to do that, but it is a way of representing that reaction rate has increased. So the forwards reaction, the left to right reaction, will increase its rate. Now we can also refer to that as shifting the position of equilibrium to the right hand side. Both of those two things mean the same. Increasing the rate of the forwards reaction or shift the position of equilibrium to the right. Both chemically mean the same thing. Now the forwards reaction uses A, and therefore increasing the rate of the forwards reaction will decrease the concentration of A, and this will result in an increase in the yield of C and D, the products. Looking at pressure next, we've got a slightly different reaction here. We've got A plus 2B forming C and D, and pressure is due to particles colliding. The more collisions there are, the higher the pressure. Now, if we decrease the pressure of this system, we need to think what would happen. So if we decrease the pressure, the system will try to increase the pressure again. And it will do that by favouring the side of the reaction that has more moles. And so we would look at this and say the position of equilibrium would shift to the left. This results in an increased yield of A and B. Now the reason why we would have an equilibrium shifting to the left is that we have 3 moles on the left hand side as opposed to only 2 moles of gas on the right hand side. So the left hand side here is the higher pressure, or would result in a higher pressure, whereas the right hand side in this one would result in a lower pressure. So if we've decreased the pressure of the system will favour the side that would cause a higher pressure. That's the side with more moles. We can look at an example reaction for pressure by taking the chemical dinitrogen tetroxide, N2O4, which is a colourless gas. It decomposes to form 2 moles of the brown gas nitrogen dioxide, as we can see in the equation below. The colourless N2O4, shown here in white, breaks down to form 2 moles of brown nitrogen dioxide, NO2 gas. Because this is a reversible reaction, the NO2 can reform into dinitrogen tetroxide, N2O4, and the process can keep going backwards and forwards. Now if we start with an amount of NO2 in a sealed syringe and pull out the plunger, what will happen? Have a think. So if we pull out the plunger and watch what happens, hopefully you can see a colour change. We'll just look at that animation again. The plunger goes out, and what you can see is that to begin with the colour goes paler. As the brown NO2 concentration goes down, it has more space, a larger volume, so the concentration is decreased. However, the increased volume inside the syringe decreases the pressure. Same number of moles of gas, more space, decrease in pressure. Le Chatelier's principle tells us that if we decrease the pressure, the system will oppose that change. The equilibrium then shifts to favour the side with more moles, in this case 2 NO2 on the right hand side, increasing the pressure and producing more brown NO2. So the colour goes paler, but then goes darker as more NO2 is formed. Have a think about what would happen if we push the plunger back in. If we were to push the plunger back in, then to begin with, it would go darker as the concentration of NO2 would increase and we'd have more brown gas close together, so the colour would be darker. But as we do push the plunger in, we're going to be increasing the pressure. And so what would happen is we'd have the equilibrium shifting to flow over the left-hand side, so it would end up being a paler gas at the end. So, activity 1, time for you to have a go. Again, thinking about A plus B forming C plus D. I want you to have a think, what will happen to the yield of D if the concentration of C in the reaction mixture is increased? Giving reasons for your answer. Pause and see how you do with that bit. So the answer to that first part is that the rate of the backwards reaction will increase because that will decrease the concentration of C, it will use C, and therefore shifting equilibrium to the left, decreasing the yield of D. Next question. What will happen to the yield of D if the pressure is increased? Give reasons for your answer. Again, pause and see how you do. So, answer for that question, there will be no change in the yield of D, and that's because there's an equal number of moles on both the left and right side of the reaction, so pressure will have no effect on this particular reaction. Bit of a trick question there. On to temperature, our next factor that affects position of equilibrium. Changes to the temperature of a closed chemical system at equilibrium also have effect on the position of equilibrium. So again, we're going to look at a reaction, just a general one, A plus B forming C plus D in a reversible reaction. But this time we're going to have a little bit of a look at some enthalpy change information. Now what we've got here is we have a negative enthalpy change. Enthalpy is the proper name for heat energy. So this is talking about how much heat energy 1 mole of a substance will produce or use in a chemical reaction. Now because this is negative, this is showing that the system loses energy. That's why it's negative. The system loses energy in the forwards direction. If we were given a positive delta H, a positive heat energy change for this reaction, it would mean that the forwards reaction was taking heat in, was gaining energy. So what we've got here is in the forwards direction, we have a negative delta H, which means we have an exothermic reaction in the forwards direction. So the forwards reaction is exothermic. Now the backwards reaction is equal but opposite. The backwards reaction will be an endothermic reaction. Now they will be equal and opposite. So if the reaction has an enthalpy change of minus 300 kilojoules per mole in the forwards direction, the enthalpy change for the backwards direction, C plus D forming A plus B, will be plus 300 kilojoules per mole. This is why you get some reactions that have a temperature change and then their temperature stops changing. It's not that the reaction has finished, it could be that you've got a reversible reaction that is now at equilibrium, and because the rate of the forwards reaction with perhaps an increase in temperature, like in this case, the rate is the same as the backwards reaction, which would be causing a temperature decrease, those temperature changes would cancel out. So let's have a look at an actual example of how we'd look at the change in temperature and how it changes equilibrium position. Another reaction here, W plus X forming Y plus Z in a reversible reaction, and we have an enthalpy change here of minus 190 kilojoules per mole. Now because it is negative, that tells us that the forwards reaction is exothermic and would cause temperature to go up, and the reverse would be the same, would be true for the backwards reaction. So let's think about this then. What will be the effect on the yield of Y and Z if we decrease the temperature of this system? Say we put the box in the fridge. Well, as we've said, the reaction is exothermic in the forwards direction and therefore endothermic in the backwards direction. It's always the first thing you've got to think about. So what will happen? The rate of the forwards reaction will increase, as the forwards reaction is exothermic and will increase the temperature. Now that increase in temperature opposes the decrease. We turn the temperature down in effect, the reaction will turn the temperature back up again. And the position of equilibrium, we can say shifts to the right. Now that's what the asterisk just means, okay, is that we've got these two things meaning the same. So the rate of the forwards reaction increasing and the position of equilibrium shifting to the right, they're interchangeable, you just need to say one of those things. So this would result in an increase in yield of Y and Z if we've increased the rate of the forwards reaction or we've shifted the equilibrium to the right, we're favouring the right hand side and therefore the yield of the products goes up. Next, catalysts and equilibrium. So we've got a reaction here, A plus B forming C plus 2D. So we can see we've got more moles on the right hand side, we've got A plus B on the left, that's fewer moles. We've got enthalpy information over here. So what would adding a catalyst do to the position of this particular equilibrium if it had been reached? You can look at the graph again and have a think about what catalysts do. So we know that equilibrium is the point at which the backwards and forwards reaction rates are equal. So for the graph that we've got here, it's currently just where the x is, where the two lines become flat. Now we know that catalysts increase the rate of a chemical reaction, and that would cause the gradients to get steeper. Now it's the gradients of both of these graphs. So what happens to the position of equilibrium? Well, absolutely nothing. It stays in the same place. All that happens is that the position of equilibrium is reached more quickly. So equilibrium is reached quicker, but there's no other effect because catalysts affect the forwards and backwards reaction rates equally. Now we're going to move on to have a quick look at industrial equilibria, just one example, which is the most common one. And we're going to look at ammonia, which is an extremely important chemical in industry. It's used to make fertilisers, explosives, cleaning fluids and loads of other chemicals. And just got a few pictures there of things that ammonia can be used to make, including nylon. Now ammonia is produced using a process called the Haber Process, invented by a German scientist called Fritz Haber, and it follows the following reaction. N2 gaseous plus 3H2 gaseous forming 2NH3 gaseous in a reversible reaction. Now, with any industrial equilibria, the correct conditions have to be chosen in order to make maximum profits. You want to make as much product as quickly and cheaply as possible. So activity 2. I want you to think about the conditions that we've looked at and the changes to equilibria. And you've got to choose conditions, one temperature and one pressure, that should be used for the Haber process and justify your answers. So there's the reaction again. Now, we have some possible conditions and you've got to choose one temperature and one pressure, as I said. Temperatures, you've got 0 degrees C, 500 degrees C and 1000 degrees C. Sorry for the strange gap there between 0 and 500. Pressures, you've got 1 atmosphere, that would be the pressure that we experience at sort of ground level. 200 atmospheres, that's 200 times normal pressure, and 400 atmospheres. And I've got some useful information. Temperature is very easy to control, you can just light a fire under a reaction. High pressures are very expensive because we need to try and prevent explosions. That involves very thick, sturdy reaction vessels, which are quite expensive to make and maintain. Fast reactions are good because that means we have quick production, we make lots of product and we make lots of money very quickly. And the final thing is that the reaction is exothermic in the forwards direction. Pause the video and have a think about which temperature you'd pick, which pressure you'd pick, and give reasons for your answers. So going through the answers to activity 2, we'll see how you did. So, considerations for temperature. A high temperature might be the first thing that you go for. People often pick the very highest temperature because we get the fastest rate of reaction. However, as this reaction is exothermic in the forwards direction, if we increase the temperature and we use a high temperature, the backwards reaction would be favoured as that would be endo. So this would actually favour the left-hand side if we used a high temperature, which means that we wouldn't get very much ammonia, we'd get a very low yield, which is not what we want. We want to be able to sell ammonia. So we might consider using a low temperature. If we use a very, very low temperature, 0 degrees, it will favour the exothermic reaction, and that would give us a high yield of NH3. But we wouldn't choose a low temperature because that would give us a really, really slow rate of reaction. And although we might end up with a high yield at the end, we'd be waiting a very long time for it. So industry doesn't like rates of reaction being very slow. Next, we need to think about pressure. A high pressure favours the side with fewer molecules. And if we look at our reaction, which side has fewer molecules? We have 4 moles, sorry I can't count, 4 moles on the left hand side and 2 moles on the right. So the left hand side would be causing a higher pressure and the right hand side would be causing a low pressure, depending on which direction equilibrium sits. So if we want if we're looking for a high pressure, it's going to favour the side with fewer molecules. We want to do that. So we want to favour the ammonia side. There's only 2 moles of gas, so we'd be looking at a high pressure. But what do we need to consider? Although this would cause the forwards reaction to be favoured, forming ammonia, high pressures are very expensive as the risk of explosion is high. So the reaction containers have to be strengthened, which costs a lot. They're not so worried about safety, it's more about the fact that it is expensive. So what conditions do we pick then? The conditions chosen have to be a compromise between the best pressure and the best temperature. So in the Haber process, the conditions used are the temperature is around 450 degrees C. That will precisely depend on whereabouts it's being made in the factory. Now that temperature is high enough to give us a decent rate of reaction, but not too high that it prevents equilibrium sitting too far to the left. For pressure, we use 200 atmospheres, the middle. It's high enough to push the equilibrium back towards the right hand side where it was shifted by the temperature, so it forms an H3, but it's not so high as to be prohibitively expensive. What we've got basically is just trying to get it sitting somewhere in the middle. Now, even taking these considerations, these compromised conditions into account, the best yield that most factories that make ammonia get is only around 15% conversion to ammonia. That's pretty good, because what they do is they recycle any unreacted nitrogen and hydrogen back in, as we can see up here. What they also do is they use an ion catalyst, which just helps to increase the rate of reaction without needing to change the conditions too much. You don't need to know that diagram, but it's just useful to be able to see it. Finally, for this video, activity 3, time for you to have a go again. For each of the following reactions, I'd like you to state and explain whether a high or low temperature and a high or low pressure should be used to maximise the yield of product. There's 4 reactions. You've got the enthalpy information. Remember that negative means exothermic in the forwards direction. Pause the video and see how you do. The answers will follow. Okay, answers then. For A, what we've got is 2SO2 plus O2 forming 2SO3. We have on the left hand side 3 moles of gas, and on the right hand side we have 2 moles of gas. So the left hand side will be a high pressure situation and we have a low pressure on the right. We therefore want to increase the pressure, as that will push equilibrium or shift equilibrium to the right hand side to favour more moles. And then if we look at the enthalpy information, we have a negative enthalpy change. Negative means that energy is lost from the reaction. So we've got exothermic in the forwards direction. Exothermic causes temperature to increase. So if we want to push it towards the products, we want to use a decrease in temperature. So we would decrease the temperature of the reaction, as that would cause the reaction to favour the forwards reaction to increase the temperature again. So we have, for this first one, an increase in P and a decrease in temperature. For B, we have 1 mole on the left-hand side and we have 2 moles on the right-hand side. So the fewer moles we have, the lower the pressure. So the left-hand side would be a lower pressure environment, and we have a higher pressure on the right-hand side. If we want to favour the right-hand side then, which is the higher pressure environment, then what we'd want to do is we'd want to decrease the pressure. That would cause the equilibrium to be shifted to the right-hand side, as there are more moles, and this will increase the pressure. We've got, in terms of enthalpy change, a positive, which means we have an endothermic reaction in the forwards direction. Now, endothermic reactions cause temperature to decrease. So if we want to favour the forwards reaction, we would want to increase the temperature, because endothermic reaction in the forwards direction which will decrease the temperature. So if we increase the temperature, the reaction will shift to decrease it, and that would be going in the forwards direction. So for this one we have a decrease in pressure and an increase in temperature. For C, we have 2 moles of gas on the left hand side and we have 2 moles of gas on the right hand side. So for C, it doesn't matter what pressure we use. Change in pressure has no effect. So it doesn't matter what pressure we would use. When it comes to the temperature, this is the same as A. We have a negative enthalpy change, which means we have an exothermic reaction in the forwards direction. That causes temperature to go up. So we would want to decrease temperature. That would be our condition, as that would cause the forwards direction to be favoured, as that will increase the temperature again. See A if you want the extra details for that one. And then for D, again we have 2 moles and 2 moles. And also what we can see here is that these are also liquids as well, so pressure is not going to actually have any effect because they're liquids anyway. But there are the same number of moles on each side, so pressure is no effect again. And here we actually have an enthalpy change of 0, which means that it doesn't matter what temperature we use either. Changing temperature, because there's no overall enthalpy change, exothermic or endothermic, there's no direction that we need to look at that, there will be no effect of the temperature either.